actually modern physics into some of this technology development. And then you will also learn how electromagnetic field is quantized and why it is quantized from micros. Chris knows about it now, right? Why electromagnetic field is quantized. You're going to give us a seminar next week, right?
Yeah.
Okay.
How's it going, Serge?
It's going well. How are you?
Long day.
Oh yeah, an exam tomorrow. Any other exams coming up?
Huh? After your exam, some final parties work on you know, one for our labs.
Yeah. Don't.
Where's Mike today?
Like,
No,
it's
it's
going to be 1-to-1.
Yeah.
Yeah. No, I know. I know.
Really?
Yeah. So I mean, it's hard to do one time.
Yeah, I know. Everyone's changing up the curriculum right now, so it should be interesting. Are we going to get one first?
Okay, let's go to chapter 9 of my book. And then after we finish that, I guess I don't have anything else to teach. Unless you request me to teach something else. Okay. So let's do chapter 9. Inverse problems.
And like recording experience is really valuable.
Yes, it's not the whole.
And also like some people don't have an advantage.
Yeah, it's everybody.
This is a rather important problem because it has a lot of applications. Oil exploration. I used to work for Schlumberger before I came here. So they were very much into this problem in the oil industry. They do a number of inverse problems different ways that they might look for a pot of oil, a pot of gold in here, they call black gold. Oil is called black gold, okay? Those actually can bring the company lots of money if they find this black gold. And there are several ways to do that. One is to use seismic. Seismic, in the past they would do explosives. They would explode a small bomb here, create a seismic wave, and then the stereo object bounce back waves. And then they put sensors. They put sensors on the surface to listen to this explosive. And then they do that over and over again. Maybe they put the explosive somewhere else, explode it, and then look for the echoes. Essentially the echoes from the earth. Okay, echoes from the earth. And there's one way to do that. And now I don't think they use explosive anymore. They just use a very strong mechanical hammer. They have this big truck that has a big hammer, and the truck just hammers the ground, create a small seismic wave. And they have good enough sensors that can pick up the echoes now. Okay. And they also can do electromagnetic prospection, EM prospection. And they can do that from the surface as well. They put electrodes everywhere. Electrodes, and then measure the current through the earth. And by measuring the current through the earth, they can solve inverse problems and figure out what is underneath the surface of the earth. Okay, so they have to solve inverse problems, and the simple electrode measurement might be just put the electrode in the ground, inject current. And then put another sensor here, sense current. And then they will put sensors all around, and then the current might flow to the earth in different ways. And then they pick up the sensor. And in order to make the electromagnetic field penetrate as deeply into the earth as possible, what must you do? what is the first thing that you need to do?
Low frequency.
Low frequency, you make the frequency as low as possible. Because the thing that dominates penetration depth is the skin depth. Skin depth is proportional to 2 over omega mu sigma. Sigma is quite large in the earth. Okay, seawater is even worse. Sigma in seawater is quite high. So in order to do electromagnetic prospection, you have to go to very low frequencies. Hertz or kilohertz. You have to work with that kind of frequency. It's actually more in the regime of hertz. Okay? And how do you communicate with submarine? If you have submarine down below the sea, how do you communicate with them?
Sonar.
What?
Sonar.
Sonar. Sonar. That work. I think sonar is too noisy. It took me noise in the sea bay. You try to use sonar communication, it doesn't work well. So if you have to use electromagnetic signal, what do you have to do?
ELF for communication.
You have to do to very low frequency, okay? ELF extremely low frequency, or ULF ultra low frequency. If actually it goes to 0.1 hertz, 0.01 hertz kind of communication in order to talk to the submarine. So you cannot talk to a submarine very fast, very slow. You cannot even send a word a minute. Sometimes in order to send a word, you have to go through many cycles or signal before you can send a bit of information. So it's extremely low bit rate of communication. And so data compression becomes a very important field if you have a speech. And if it's coded in terms of bytes, megabytes, the people will want to compress it down to just a few bits so they can send information. So data compression becomes very important. But the oil industry is better, does not suffer as much loss as the people in the submarine world. Okay, but one of the recent things that happens after I left the oil industry, I left the oil industry about 1985, and after I come here for almost 30 years now, lots of new technology has developed in the oil industry. One of this is the wireless telemetry. You figure out how to send signals back and forth from under the earth up to the surface of the earth. But it also figure out a way of controlling drill bits. It's a wonderful technology in the sense that one of the things that has developed after I left the oil industry is horizontal drilling. When I was there, one way to prospect the depth of the earth is actually to drill a borehole, a well, or a borehole into the earth. And because of the skin depth effect, you can only see very short distance and at only very low bit rate. But if you drop a sensor down here, put sensors down here in this borehole, then you can actually probe the surface of the earth, the depth of the earth a lot more easily with borehole sensors or well sensors. And then they can tell you whether you hit oil or you don't hit oil. And 20 years ago, they only drill horizontally, but now they only drill vertically. But now you see in pictures from the oil industry, they have a rig here, and then they have a well, and then we can drill in this manner. We can drill in all directions. Okay. That's called horizontal drilling. That was not there 20 years ago. And the reason why they can do this is because they know how to control the drill bit. They can know how to steer the drill bit. Drill bit steering. You know, at the bottom of the drill, they have these teeth, right? I don't know how to draw them very well. They drill into the rock. And now they can figure out how to change those directions by wireless telemetry. So they have something up here It's like the brain, a CPU up there that controls this thing. But this thing talks to the people up on the ground surface at a very low data rate. They don't have to send data rate very high, but this thing can control this bit at a higher data rate because they're not too far apart. So they can tell this drill bit to go left, right, or whatever, and they can drill into the neighbor's oil field. So there's a lot of lawsuits going on now because you're stealing my oil, I'm stealing your oil. Okay. If you're in Brunei, you can drill into Malaysia. Steal Malaysia's oil. Okay. So lots of things like that happening now. So that is the oil industry and what has happened in the recent 20 years. But inverse problems still remain a very important problem. Of course, when you have something like this and you have geological base, you have to solve very complicated electromagnetic problems in this complex structure. So if you want a job with the oil industry, there's still plenty of jobs. If you know how to solve Maxwell's equations well, they would love to have you. Okay. So let's talk about inverse problem. Go back to talk about inverse problem. And there are essentially two kinds of inverse problem. One is linear inverse problem, and the other one is nonlinear. Nonlinear doesn't mean that the physics is nonlinear. It just means that the scattered field is nonlinearly related to the incident field. Okay. So linear inverse problems exist in like synthetic aperture radar. It's actually a very good example of the use of inverse problems that are linear. Magnetic resonance imaging, okay, is another example of good inverse problem. Another one is actually ultrasound, okay, ultrasound. And well, you can see that what you do in optics now, optical coherence tomography, is a kind of inverse problem that's linear coherence tomography. Okay, X-ray tomography, right? What is the acronym for X-ray tomography?
Macro CT.
What is that?
Macro CT.
Micro CT? What is that? What is the acronym they use for X-ray tomography? XRT or something else? I don't remember. Okay, X-ray tomography. Okay, all those are linear inverse problems. Many of them are linear. So if you learn some linear inverse techniques, you can actually understand a lot of technologies that we use. And let's talk about nonlinear inverse problems. Why are inverse problems nonlinear? Actually, we can explain the physics quite easily. Nonlinearity comes about from a number of physics. One is multiple scattering. Okay, source of nonlinearity. Say if I have a object producing a scattered field, I have an incident field, and then I have a scattered field here. Okay, I have object 1. And then it produced scattered field 1. And then I do a second experiment with object 2. I have incident field here. And the scattered field, which I call E scattered 2. Okay. And then I do an experiment with both of them together, object 1, object 2. And then shine an incident field in. I get a scattered field here. Is this scattered field the sum of the previous one? Are they the sum of the previous two experiments? No. What is the reason for the fact that the third experiment is not the sum of the previous two? What physics destroys that?
There can be a coupling between the two.
The what?
There be a coupling of the scattered.
The coupling of the scattered, it could be multiple scattering, right? There will be scattered field of object 1 and the scattered field of object 2, but then there could be multiple scattering between them that produces another scattered field, right? So this is not possible. So the scattered field is not linearly proportional to the object from a linear system theory viewpoint. So in order to assume linearity, you have to make assumptions. One assumption is that there's no multiple scattering. There's only single scattering. If there's only single scattering of an object, then you can get a linear problem back. But if you have multiple scattering, then linearity is not possible. Another way that you can see that nonlinearity comes about when you're in the ray physics regime is due to multipath. Okay, if the reason why many of this, like X-ray and ultrasound and so on, are linear is because you assume that the signal only goes through the object once. Okay, like at very high frequencies, you can assume that X-ray just goes through the human body straight. And you can prove that the field here is linearly proportional to this object. There's a linear function of this object. But if there are multipath effects, like if the thing goes like this and then goes like that, the linearity thing is lost. Okay? So let's construct a very simple linear inverse problem that we often see in X-ray and ultrasound. And in order to see this inverse problem, we have to use ray physics, sort of. Ultrasound, X-ray, and even MRI. MRI actually comes about for another reason that you can do a linear inverse problem there. But in this ultrasound and X-ray, what happens is that the frequency is extremely high. So you can use ray theory. So if you have any object, then you can essentially assume that the wave just goes through the object in a straight line, or a straight line that is not curved very much. And that happens at high frequencies. And then the phase of the wave as it propagates, it's just cumulative. So you have to picture that the field is proportional to e to the I omega s of z prime dz prime, from z naught to z, say, from A to B. Say it propagates between 2 points A to B. The phase of the wave just accumulates in this manner. This is a very simple ray picture. Okay, so this is what we call the slowness. Slowness is 1 over velocity. Okay, the faster you are, the smaller is your slowness. There's some language that they use in acoustics. Okay, and if you're very slow, that means your s is very large, your velocity is very small. Okay, but this is just a cumulative phase accumulation.
But why are we assuming our rate is of that form?
Because it goes like a ray through this object, and I call this the z prime x. The ray will just accumulate in this manner, right? So let me give you another physical picture. So if I have a layer material, and if I send a wave through here from free space to this layer material, and this is K1, this is K2, this is K3, and so on. When it goes through the first layer, the phase that it accumulates will be delta Z. Let's assume that this is delta Z, right? And then if it goes through the second layer, the phase that accumulate will be A2 delta Z, and so on. And then you keep accumulating the phase in this manner. Okay, so finally this becomes something like either IK0Z plus I A to B K1Z dC kind of thing. So you get this physical picture. What is assumed in this physical picture? There's no something is absent in this physical picture, right? What is it?
No loss.
No reflection, right? No backscattering. The wave just goes through straight like that. X-ray does that. So when you go to very energetic photons, very energetic waves with very high momentum, they scatter very little backward. The particle just goes through. And you can use this picture to describe X-ray. Or ultrasound. Ultrasound has very short wavelengths as well. Okay? So this is almost like the WKB picture. So I give you a take-home exam to do on WKB. It's a very simple technique to learn, and many of you have learned about WKB in other courses. So it's like regurgitate and reproduce. You just read my book, and then you can answer the question. And then turn in your take-home exam for that part. But hopefully you will learn what WKB method is. Okay. So WKB picture gives you this kind of picture, that the wave just propagates without reflection. Just goes through the medium with very little reflection. And then you can measure in the case of X-ray, the attenuation. In the case of X-ray, this number is purely imaginary, so it's mainly attenuated. The phase is not important in X-ray, because in X-ray the phase is so small, so it becomes a random number. But attenuation can be measured as X-ray goes through the human body and so on. Okay. So in X-ray, this is more like minus alpha Z kind of thing for X-ray. You actually measure the attenuation. But for ultrasound, you can measure the velocity. You can measure the time lapse between 2 points. Okay. So we can define a kind of delay. Time delay in ultrasound, the kind of attenuation in X-ray that we define to be tau is the integration of the slowness between 2 points S Z prime dZ prime. Okay, you integrate the slowness, you get this time delay. This has a dimension of time. Okay, so you can perform this experiment either X-ray or ultrasound, where you have the coordinate system. This is more true of X-ray because X-ray does propagate in a straight line. Ultrasound, less so because ultrasound is lower frequency compared to X-ray. So I have a whole bunch of transmitter here, a whole bunch of receivers here. This could be X-ray transmitter and X-ray receiver. And this could be an X-ray film. FILM. Like in olden days, they do that. I don't think they do that anymore. They just use probably other kinds of X-ray detectors. What do you call those camera that you have? The guy got the Nobel Prize for charge coupled device, right? Yeah, charge coupled device. They probably use something like that to detect X-rays these days. CCD camera, put it there. Everything is digitized. And they told me X-ray is very safe now. My dentist keep telling me to have more X-rays for my mouth because they say it's very safe. You can do it at very low dosage. And absolutely I don't have to worry about it. In olden days, we have to put a huge dosage of X-ray and then we collect it with a drop. Okay. So you can think of that measurement as a projection. That this slowness actually is a function of position. If you think of this picture, and that X-ray collection is actually taking a projection of this thing. This is called projection. Okay, you take a projection of this. Essentially, you pick y prime to be fixed, you just integrate along x prime. Okay, that's called a projection. And over here, you get a projection which is a function of y prime. Okay? Now let's say if you have this projection, what can you do with this projection? You can actually do something very wonderful. You can relate this projection to the Fourier transform of this in a very simple manner. Like say, if I were to write this as a Fourier transform, decay x prime, decay y prime. Okay, just use prime coordinate to mean that. And then its Fourier transform, which I use a capital letter for, e to the I k x prime, x prime plus I k y prime, y prime. Okay? And if I were to plug in the Fourier transform of this, I can write this as a Fourier transform. Okay? I can write py prime as being equal to an integration of this. If I were to plug this into the above and integrate with respect to x prime, if I integrate with respect to x prime, what do I get? Plug this into the above, integrate with respect to x prime, what do I get? I get a delta function, right? Yeah, I get a delta function in kx prime, right? Something like that. If I was to plug this in, integrate with respect to x prime, I get a delta function. And then after that, I use the shifting property of the delta function and convert this into an integral. And then I have this this thing just being equal to that. A projection is actually equal to a Fourier transform of a slice of this Fourier transform. If we plug this in, integrate, this becomes a delta function. Only kx is equal to 0 is important when it's a double integral. Okay, I'm left with this being equal to that. Can you see that? Can everybody see that? Or you need to go into the detail. So this is very nice. That means that if I collect this data with this X-ray form and Fourier transform it, I get a slice. I get a slice of this Fourier transform. Right? I get a slice of this. So you have to understand this formula. This formula is quite easy to apply. Plug this into above, do the dx prime integration, use the shifting property of the delta function. Okay? Do one of the kx prime integrate, close form, then you get this formula. Then I let you digest that formula a little bit. So with one projection, you get one slice. But if I want the whole of this in the Fourier space, what must I do? I only got one slice of this with one experiment. If I want to have more slices of that, what do I do? Yes, very good. Rotate my experiment. Do another experiment. Okay? So you can think of this as that this thing has a Fourier transform in the Fourier space. Kx prime, ky prime. And the Fourier transform of this, say, is something like this. Okay? So one experiment gives me a slice of this. If I use a line like that. I get that Fourier data. I rotate my experiment, I'll get another slice of the Fourier data like this. Right? I rotate, I get another slice. And then I fill up this object now by rotating the experiment 360 degrees. And then I obtain all the Fourier data about my object. And having obtained this Fourier data, I do some interpolation, I do some signal processing, I get back my object. Okay, from this. From this you get like just Fourier transform x prime, y prime. So this is called the slice projection technique. You get the projection, you get a slice of the Fourier data, rotate, get another slice, project again, project, slice, project, slice, project, slice, and then I think it's called projection slice theorem or project slice projection theorem or something like that. And this is how X-ray tomography works. Okay, very simple. MRI also works the same principle. Very clever. But the reason why you get the slice in MRI is quite different. Okay, so. Are there any questions on this? Yes?
So do we assume the object is homogeneous or isotropic?
You can be inhomogeneous. You just assume ray theory works. That ray theory works. X-ray goes through an homogeneous body just like a straight line too.
But in the slowness, the material problem is actually divided in the slowness.
Right.
Because I omega integration of S is 1 over V. So
Right.
we have epsilon mu in the slowness.
Right.
So, but if you rotate it, well, wouldn't the rays seem different?
No, let's assume that this is an X-ray experiment. Then instead of constructing the slowness profile, you construct a attenuation profile. This attenuation profile of the human body does not change with your X-ray machine. The X-ray machine rotates, but you're still human, right? You're still, you know, still yourself, right? Still yourself, it didn't change. Would your attenuation change inside you when your X-ray machine rotates around you? No, right? You assume ray theory that the ray goes through the human body like a straight line. Okay, that's the only assumption. And that's very good for X-ray. Not so good for ultrasound. Because ultrasound wavelength is finite, not infinitely small like X-ray. But it's very good for MRI. And you will have to learn the reason why this slice projection theorem works for MRI. It's for a very different reason. Not because of ray theory nor wave theory or anything, but very clever engineering design. That's why Otto got the Nobel Prize. After he got the Nobel Prize, another person argued with him. He said, I also deserve it because I get the same idea too. Do you remember that after he got the Nobel Prize? Maybe you guys were not at Illinois yet. The guy published a big page in New York Times saying that I deserve the Nobel Prize as much as Waterloo. Okay, he has the New York Times article explaining why so. Okay, so this idea works very well for MRI and X-ray, approximately so for ultrasound. Okay, and people use this technique anyhow for even when ray theory does not hold true, approximately hold true, then they still use it to get an image. It's an approximate image. Okay, so because of the fact that you can go back and forth between these two things, there's something called the Radon Transform. There's something called a Radon Transform that connects these two, and we'll derive Radon Transform. And we'll first do that in 2 dimensions, and then I ask you to do that in 3 dimensions in the take-home exam. But actually, it's just regurgitate and reproduce because I actually show you how to do the 3D case in the textbook. You just read it and then reproduce it, so it's not that difficult. But let me show you the 2D case. We have 10 minutes to do it. Let's see if you can do it. 10 minutes. So this relationship is actually quite true. Okay, this relationship is actually quite true and straightforward. I can write that relationship in cylindrical coordinate system in 2D. Instead of x and y, I can write it in terms of rho and phi, and then change the right-hand side to cylindrical coordinate system as well. So if I do that, then I will have something that looks like this on the right-hand side. and then multiply by this phase factor, which is just a plane wave factor, into the ik rho cosine of alpha minus phi, and then s of k rho alpha. So this capital S is the Fourier space one, the other small s is the coordinate space one. And this relationship can be written as such. This is a plane wave factor, and essentially this is a k vector in the Fourier space, and this is a coordinate vector in real space. And then this angle is called alpha. This angle is called phi. And if you work this thing out, it will look something like that. So everything is actually done in cylindrical coordinate system. You look at the experiments, they're all done in cylindrical coordinate system. So it's better to convert this back to a cylindrical coordinate system. And then you can show that this data collection process is actually like you getting a slice of the Fourier data, okay, and then you can relate this Fourier transform to the Fourier transform of a slice. Of the Fourier data in this manner. Okay, you can actually write sk rho alpha related to the projection in this manner. This is actually taking a slice and just writing this in the general coordinate system. I'm just rewriting this from over here. In the general coordinate system, we're taking the Fourier transform of the expression and rewriting it in a general expression. Because C is some coordinate system